want to thank you all so much for sharing this time for me. And I realize that your lunch comes after this and we're late. So thank you. So all of you sitting out there right now, and me up on stage, are breathing. Every human breathes. You're going to breathe many, many times during my talk. But sometimes, when you breathe in addition to taking in the oxygen you need, you're going to breathe in a virus, a respiratory virus. So what are viruses? We know the term, we've been through pandemics, but what is a virus? It's a tiny, tiny particle, so small we cannot see it with a normal microscope. And it's something that needs a place to land and grow, and that's often humans. And it gets inside our cells, and it uses our cells and our bodies to copy. So scientists have spent many decades trying to understand these viruses, and we've made a lot of progress. On this slide, I just show you, I said you can't see it with a normal microscope, but how can you see it? Well, you can see it with very specialized microscopes, electron microscopes, cryo-electron tomography, ways like that. This just shows you a few respiratory viruses. On the left is rhinovirus, causes your common colds. Then you see influenza virus. We'll talk more about that one. SARS-CoV-2, you probably all know about that one, and respiratory syncytial virus. These are just examples, so we can get an idea of what they really look like, but only with very specialized equipment. What do they do? Well, sometimes they don't do much, right? Sometimes you'll breathe one in and you'll have nothing happen. And that's because sometimes you're already had that virus. You're not going to get sick again. Or sometimes it's a virus that's not going to make you all that sick. Many viruses that you come in that way, they just cause runny nose. You get a cough. You have to blow your nose. But then you feel better. But sometimes it goes further than that. Sometimes, for instance, you'll start to get very sick. One example of this would be respiratory syncytial virus, or sometimes RSV. For many of us, it's a pretty mild infection. But for some people, especially if you're older, if you're very young, or if your immune system has issues, RSV might put you in the hospital, RSV might kill you. And thankfully, we finally have a vaccine that we can use in elderly, and we're starting to develop things for others for RSV. But it's a very serious pathogen in many people. And sometimes viruses go much further. They make many people in the world sick, and they're very, very serious. In the last 100 or so years, the biggest example of this actually wasn't the recent pandemic, it's the 1918 flu. In 1918, a new strain of influenza virus entered the human population, and none of us were ready for it. None of us had protection for it. So during World War I, it was already a very stressful time, and it was horrible. They estimate that in the 1918 flu caused about a third of the world's population to get sick. There were 500 million people in the world then. About a third of them got this virus and got sick. About 50 million of those died. That's about 10% of the population of the world. If you look around this room, think about 10% of the people in here dying. That's a lot. And that's the kind of thing a virus could do. Another major example, of course, that you all know of what a virus could do, we've recently lived through, and that's SARS-CoV-2. And this just shows you from last week what the World Health Organization said about reported cases. On the top is the US, reporting at least 103 million cases of SARS-CoV-2. Chile reported about 5.5 million cases. Many of these cases people had, they probably never reported. But it was everywhere, and we all know it changed our world. But those aren't the only examples. We constantly have new viruses that enter our population. In this slide, you see a timeline from 2000 of just some of the outbreaks that we've had to watch and be very careful and worried about, things like Ebola virus and Zika virus that came out, and we need to know how to handle them. And also especially, if you look up here, we had in 2002, what is the original SARS? And then in 2012, we had what's called MERS, Middle East Respiratory Syndrome, very related, all very related to our newest pandemic virus, SARS-CoV-2. All right, so I hope I haven't scared you too much, but the reality is most viruses were not going to hurt you that much, but sometimes what we get is something very serious. So how do we handle it? What do we do? Well, the good thing is we have approaches. The most important thing to remember is that knowledge about viruses and knowledge about what might happen and how we might deal with it is the most important thing. And that's knowledge from scientists, knowledge from people who are not scientists but who will live through this. So I so appreciate you being here. And it's one of the reasons so many people like myself, who's a virologist, spend so much time trying to understand how do viruses work. So we really need to figure that out. If you have a new virus, the first thing you ask, they ask for SARS-CoV-2. What's related to it? What might may do? What might be similar? And in that case, they could look and go, oh, SARS was related, MERS was related. We have some research on those already. We can hopefully start to figure this out. And so they use those as examples. And then you target two major things. And you've probably heard about these. First is vaccines. A vaccine protects you from ever getting the virus. Very, very important. Then you go after antivirals. What's an antiviral? It's a drug you can give a patient who has the virus. And sometimes someone hasn't been vaccinated. Sometimes someone has immune suppression and their vaccine doesn't help them. So antivirals also become really, really, really important. And in both cases, what we already knew was so critical to where we could go. Now, I'm not going to talk much about vaccines today, because probably many of you have been vaccinated with COVID vaccines. You know a lot about it. But we drew extensively on knowledge we knew about what was already out there to do this. And in fact, the first vaccine candidate went into a sample population within something like 6 weeks of having the sequence of this virus because we already knew so much. So I'm going to spend a little more time talking on antivirals because it's something people know less about. But they're hard. So let me talk a little bit about antivirals. What is an antiviral? It's a drug you give someone who has a virus, just like we give an antibiotic to someone who has a bacterial infection. Antivirals are actually really, really hard to develop. And that's an important message today. We only have antivirals for a small number of viruses. We have a lot for HIV. We have ones for flu and herpes and the hepatitis viruses. And that was about it prior to SARS. So we'd failed with a lot. We were still trying to come up with things. And some of the ways we tried didn't work. With antibiotics, they had big programs where they just simply took, lots of thousands and thousands of plates of bacteria, and they would dump something on it and see what died. But it turned out it doesn't work for antivirals. They had plates of cells, they infected them with virus, they dumped things on, and even after doing many, many, many screens, they only found one drug. And that was something called amantadine, which hit influenza. But now every strain of influenza in the world that we seem to see is resistant to amantadine. So that doesn't work. So what does work? What works is to figure out exactly what happens when that virus gets in a cell and figure out how could we stop it. And how can we stop it without hurting the cell? Because we're giving this drug to a person, and we don't want to hurt the person at the time we hurt the virus. So what you have to do is figure out how it really works. And certain proteins certain targets have been the best. So let's look. You do not need to know all these details, but this is just a life cycle of SARS-CoV-2. And what would we guess at the beginning? What did we know? Viruses come into cells, and then SARS-CoV-2 is part of a family of viruses that all start by making a very, very long thing called a protein. It's the thing that helps do all the processes they need. But instead of making short ones, they make a big, 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 big long one. And then they make something called a protease. A protease is something that cuts that into pieces. So you make your big long one, that doesn't work, it won't do anything, then you cut it into pieces. And so that part up here is one potential target, and in fact, proteases are great targets for HIV. Then eventually you go and you make new copies of your virus. And that's actually a great place too. We had a couple other viruses like HIV and herpes viruses where targeting polymerase worked, targeting replication. And then eventually you'll assemble and you'll leave. Now, any of these could be targets. But I told people in the March of 2020, when we knew about this, that the most likely targets for this new one would be the same targets as before, proteases and polymerases, the things that do cut the protein into pieces, the things that do replication. And Now, all these years later, people studied every bit, and every bit is worth studying. But what they found is the following. So SARS-CoV-2 has two big proteases that are really, you have to have them for the virus. They're different than the cell. One of them, called 3CL, is the target for probably one of them, but we have 3 effective antivirals now. Something called Paxlovid, at least that's the name in the United States. It works quite well. You give it as a pill to people. And it's now been approved in the US. They're trying to find more inhibitors, but that one is a great one. What about others? Well, they've done replication, and lo and behold, that's also a good target. We have 2 great drugs that target that one. One is called remdesivir. You have to have it intravenously, so it's not easy to use, but it does work, and it is used. The other is called molnupiravir, and it's used a lot. So we have 3 antivirals right now, and development of them follow the same process we would have expected. So what that tells you is knowledge matters. So in the last few minutes, I want to now talk about a new virus, and then we'll talk a little bit about work on this one, and partly because my lab is one of the labs in the world that works on this, partly because you might have read about it in the news recently. There's been a lot of stuff out there worried that human metapneumovirus might be causing the next pandemic. I've been called by journalists to ask about this. The top line, doctors say this is the most important virus you've never heard of. That actually came from May of 23 in the United States. These lines down below are just the last month. They're monitoring it. Everybody's worried. They all think HMPV might be a problem. And since HMPV is a virus I work on, people call me a lot. And they ask me, are we going to have a pandemic from HMPV? And my answer is, I really don't think so. Why? Well, this isn't a new virus. This is a standard respiratory virus. It can make people very, very sick. Elderly, very young, immunocompromised, make you very, very sick. It's related to respiratory syncytial virus. But we've almost all had it. Almost every human on the planet gets it by the time they're 5. So almost all of you have protection of some kind to this virus, which means it's not a very good virus to cause a pandemic, because most of us have protection. It is a virus where we see cases every single year. The Centers for Disease Control in the United States actually monitors this completely to check and make sure that they understand what's going on. It's one of the 5 or 6 respiratory viruses. You can just go on the website and see how many cases we have in the US. It's common. It was identified in 2001, but honestly, it's been around a lot longer than that. So what does that mean? It means we have to know about viruses to know if we're afraid. In this case, I am not afraid that HMPV is the next pandemic. Nothing says it's a brand new type we've never seen before. It's just something we all know we have to live with and we have to figure out to stay healthy with. But it is important to figure out what you would do if it suddenly became more dangerous, if it had mutations in it that made it more dangerous or things like that. And so my lab really focuses on how do we understand this. I'm just going to tell you a couple little bits to give you an idea of the kinds of work we do to study these viruses. So this is what we call the life cycle, or how HMPV works. It binds to a cell surface and comes in, so it gets into your cells in the respiratory tract. Now this is a type of virus that doesn't have a protease. It doesn't use that pathway. So you would know, oh, we don't develop those because that won't matter. But it does, as soon as it comes in, have to figure out how to do replication, how to make new copies. And then eventually it has to figure out how to go out and make copies and take them out to the rest of to a new cell or a new host. All right, so how can we study that? I'm just going to tell you 2 snapshots. No one really had studied much about either replication or spread when my lab tried to do it. So I've just a couple of pictures for you. This is Nicolas Cifuentes, who was a postdoctoral scholar. He's here in Santiago. He's from Chile. He came to my lab for 5 years, and this is some of his work. He infected cells with 3 different types of HMPV. And then he used a special way we can stain where we can actually measure the viral RNA. We can see viral RNA. So if it's red, that's RNA from the virus. That's its genome. You can see the gene right there. And then there's a critical viral protein here, and then yellow would be where we have everything we need to do replication. That's the replication body. So he was able to see them. We were able to study them. And just one fact about them I want you to remember. Those replication bodies, they're really, really movable. They move around, they move in cells. Here what you can see on the top is some other thing is coming in and it's just becoming part of it. It just engulfs things in. Down below on the bottom, things leave. So it's very dynamic, it likes to move around. Now remember that for the next part. Another thing we've looked at in the lab is what do these viruses look like and how might they move to cells? Nobody really knew. So for that, if you want to know what they look like, you've got to go to electron microscopy. And here, Farah was a graduate student. Santiago was actually an undergraduate at Columbia in my lab. And what you see on the top, we're using electron microscopy, a special type of it, that's just cells that are not infected. And down below, that's an infected cell. This is human cells. And what you see is suddenly all these big things coming off, like little snakes or worms coming off, right? That's virus particle coming off cells. Thousands and thousands will eventually come off. And so we could map what happened, how their structure is, all those things to understand what they'd look like. But the other surprise we found is that human metapneumovirus, when you infect cells, about 80% of the time, it causes cells to change and to now extend and touch other cells, okay? We call it an extension. It's a connection. It forces cells to make new connections. And so we asked ourselves, why? We came up with an interesting hypothesis. I told you in the first part of, we got these replication bodies, they like to move around, right? Well, maybe they could move all the way from one cell to another. And so, this just shows you an example of that. The arrow points to a replication body, and you can see that it actually moves. It was in one cell to begin with, and it'll move down into another cell. In fact, we actually look at these under a microscope for like 8 hours, and we can watch things move. And this is one of the first examples of a virus spreading one cell to another just with a new mechanism. It doesn't even have to go out and in, it just moves on. And knowing those things will help us understand what's going on. All right, so what are our take-home lessons today? So this just shows you that mechanism. It could go out and in, or it can spread right from one to another. 2 ways we'll have to fight it. All right, what are our take-home messages? Respiratory viruses are a constant part of life. You're always going to see them. They can cause very mild illness. They could cause serious illness. Sometimes we'll get pandemics. If we want to deal with those, the more we know, the better. The better prepared we are and the better we are ready to make vaccines, ready to make antivirals, the more the public is ready to know what they have to do in these cases. And so we as scientists have to develop the details, the understanding, so we can so we can study all those and get ready for anything that comes. And with that, I want to thank you for your time and wish you all a wonderful lunch.